Here is problem 2518 from your homework, and in this problem you are given the resistance of the wire 3.2 ohms, and it's bended in two loop in square shape, and you are given the size or the length of the two loop 9 centimeter, and the second one is half of it, so 4.5 centimeters. The magnetic field is shown increase rate. So I have now magnetic field increasing rate, and we have 0.05 Tesla per second, means magnetic field divided by second. They ask what the current, the wires, and what the directions flow in the large loop. So here in this problem, we can determine the rate of the change of the flux through each loop separately. If we can combine those two rates of a change, we could find the EMF from there. And then we use the Ohm's law, will give us the current. But the only thing is here, we need to be careful. We need to combine the rate of a change of the flux in two loops, but we have to careful to consider the direction of the current that could be induced by change of its square. So according for the Lenz's law, we have the increasing magnetic field. So in that case, the induced magnetic field will be pointed out into the page. So we have magnetic field point into the page in both loops. So now we're gonna use the right-hand rules to find the direction of the current. So the hand rules for the big square rule, a square loop, right hand, your hand pointed into the page, and your thumb will be indicate to the direction of the current. So in that case, we have the direction of the current will be clockwise current, this direction. Similarly, in this small square will be clockwise. Now we ask how to be careful. Look at the direction for the current and for both two loops. Even they are both and they are clockwise, but they are in different directions here. One to the right, one to the left. So here you have to not add the two flux, you have to subtract. So basically what that means, we have the phi total. In that case, well, phi from the large loop, subtracted the flux from the small loop. That's the only thing you have to be careful with that. Beside that one, now we given the directions, we know what we are doing, so we can move on to find our. So we have delta phi divided by delta t, which is the EMF. I can write down delta phi, which as a function with the magnetic field area, times delta b divided by delta t cosine phi, cosine theta, where theta in both cases equal 0. So now we can write down the general electromagnetic field, or the EMF generally from these equations here. This delta phi will be delta phi for large divided by delta t minus delta phi for large for the second part, delta phi for small divided by delta t. area of the large from this one here times delta P for the large loop, or are the same. So both of them, they are the same. The only difference here, we have different area minus A small or small loop delta P, since they are both of them, they are the same. So here now what we have, just plug the number in my equation to find the equation. So the area for the first one, 0.09 meter square. This is the square loop. Times we given delta P by delta T, which is 0.075. So this one will be the same for both cases. 0.075 Tesla per second. This is the first part. Minus, only difference when the second one will be 0.045 meter square times my magnetic field ratio will be, and here is the, just to confirm that, here is the theta equal 0. So cosine theta will be 1. So that's why I don't consider it in my equations here. Tesla per second. So Mr. Write down the unit. So according for my calculations, it will be 4.6 power, 4.6 power to the minus 4. As a unit will be volt. Then I can use the Ohm's law to find my current, or my induced current will be E divided by R. We are given the E, or the EMF, 4.6 power to the minus 4 volt divided by 3.2 amps, and that answer will be 1.4 power to the minus 4. 1.4 power to the minus 4 amps. Okay, so this is the only thing we need to consider. The key point here is this confusing one. You think maybe I can add it, but you cannot figure it out until we get the direction for the induced current using right-hand rules. Then, oh, they are in 2 different directions. So I end up with the subtract instead to the addition. Okay, thank you.